Dear students, hope you are all doing fine. Today, I, Dr. Pushpal Ghosh, Assistant Professor, Department of Chemistry, Dr. Horising Gaur Center, University Sagar, will deliver a lecture on a very important topic, Postulate of Quantum Mechanics. The content is written by Dr. Moutushi Manna, Senior Scientist, Central Salt and Marine Research Institute, CSMC Rai, Bhavnagar, Gujarat. In this module, you will learn interpretation of wave functions, nature of wave functions. The state of a system is completely specified by its wave function, which is explained by postulate 1. Then I will explain quantum mechanical operators which represent classical mechanical variables, and I will come to postulate 2, 3 and 4. Then I will explain postulate 5, which is known as the time dependence of wave function, which is governed by time dependent Schrodinger equation. Then I will explain postulate 6, and then I will summarize my lecture. So far we have learned that the variables of classical mechanics are represented in quantum mechanics by operators. The operators can operate on wave functions to give the average or expected results of measurements. Now, we will develop various conjectures that we have made earlier as a set of postulates, and then discuss some general theorems that follow from these postulates. It is like developing a set of axioms in geometry and then logically deriving the consequences of these axioms. Before jumping to postulates, let us discuss about interpretations and nature of postulates. We have learned that Schrodinger equation as H psi is equal to E psi x, where H cap is called the Hamiltonian operator, psi x as the wave function, which is called as eigenfunction, and E as the energy and eigenvalue of the Hamiltonian operator. The basis of the importance of psi is a suggestion made by Born in 1926 that psi star psi is equal to mod psi square, which should be regarded as a probability density. This suggests that in the case of one dimensional system, the particle is free to be found anywhere along a line. Let us divide this line into infinitesimal segments of length dx. You can see this figure in screen. Then the probability for the particle in the line segment between x and x plus dx is psi x star psi x dx is equal to psi square dx. It is to be emphasized that psi star psi is equal to mod psi square is not itself a probability, it is a probability density in the sense that it gives the probability when it is multiplied with the volume of the origin of interest. In case of 3 dimension, the wave function depends on the coordinates x, y, z or collectively r, and Born's interpretation of psi r is that psi r star psi d tau is the probability of the particle being in the infinitesimal volume d at the point r. The normalization condition, which I will explain later in later sections, imposes certain restrictions of the wave functions. The wave function cannot become infinite over a finite region of space, as shown in figure 2 in the screen. For if it did, the integral over area under the curve psi star psi would be infinite and the Born interpretation would be untenable. This, however, does not rule out the possibility that the wave function could be infinite over an infinitesimal region of space. If psi star psi is to tell us the probability density of finding the particle, then it must be single valued. It would be absurd if psi star psi could take on more than one value, which you can see in the figure 3 on the screen. There cannot be 2 or more different probability densities of finding the particles at a particular point. In simple applications, the single valuedness of psi star psi implies single valuedness of psi. The Schrodinger equation is a second order differential equation, and for such a derivative to exist, it is necessary that the function must be continuous. Therefore, psi must be continuous, and also the first derivative of psi must also be continuous, though it is a weak condition. Now, I will explain the state of a system is completely specified by its wave functions, which is normally postulated by postulate 1. Normally, classical mechanics deals with the quantities known as dynamical variables, such as position, momentum, angular momentum and energy. Also, a measurable dynamical variable is called an observable. In classical mechanics, we can specify a state of a system by giving 3n positions and 3n velocities or momenta coordinate. But this is not happening in quantum mechanics, because the uncertainty principle tells us that position and momentum of a particle cannot be determined simultaneously with infinite precision. Though classical mechanics is useful for macroscopic bodies, uncertainty principle has no practical importance for those. However, for small bodies such as electrons, atoms, molecules, the consequences of the uncertainty principle are far from negligible, and concept of classical mechanical picture are not valid. This leads to our first postulate of quantum mechanics, and the first postulate, which is called postulate 1, state of a quantum mechanical system is completely specified by function psi r t that depends on the coordinates of the particles and on the time. This function called the wave function or the state function, which has the important property that psi star r t psi r t dx dy dz is the probability that the particle lies in the volume element dx dy dz localized at r at the time t. So, we can write integration psi star r t psi r t dx dy dz is equal to 1, which is known as equation number 1, or integration psi star r t psi r t d tau is equal to 1, which is known as the equation 2, where the integral is taken over the entire space. In addition, psi r t must be well behaved. That indicates that in addition to being normalized, psi r t and its first derivative be single valued, continuous and finite, which I have just explained earlier. Now, let us take some examples to determine whether the following functions is acceptable or not as a state function over the indicated intervals. For example, e to the power minus x in the range of 0 to infinity, whether it is a state function or not, answer is that it is a single valued, continuous and finite and quadratically integrable over the range, and hence it is acceptable. Now, let us another example, that e to the power minus x in the range of minus infinity to plus infinity. This value is not acceptable, because it cannot be normalized over the interval in the range of minus infinity to plus infinity, because e to the power minus x diverges as x to infinity, and of course, for this reason it is not acceptable. So, you find that e to the power minus x in the range of 0 to infinity is acceptable. However, e to the power minus x in the range of minus infinity to plus infinity is not acceptable. Now, I will explain another very important set of postulates. The quantum mechanical operator represent classical mechanical variables, which are the basis of the postulate 2, 3 and 4. Now, what is postulate 2? It tells that to every observable in classical mechanics, there corresponds an operator in quantum mechanics. It can be more precisely stated as postulate 2 prime, which states that to every observable in classical mechanics, there corresponds a linear Hermitian operator in quantum mechanics. Now, let us see some examples of the correspondence between the observable and the operator, which I have presented here in the table 1, which tells about the classical mechanical observables and their corresponding quantum mechanical operators. Now, in this table you can found that for example, for position it is an observable, but in the operator it is x cap, where the operation is multiplied by x. Similarly, when we are going to the momentum px, it is operator is px cap and operation name is minus I cross del by del x. Similarly, for kx operator is kx cap, for ux operator is ux cap, and for total energy, when we are considering total energy as observable, its operator is h cap, which is known as the Hamilton operator, and this can be explained as minus h cross square 2m del square by del x square plus del square by del y square plus del square by del z square plus u x y z. Now, I will explain postulate 3. In any measurement of the observable associated with the operator a cap, the only values that will over be observed are the eigenvalues small a, which satisfy the eigenvalue equation. Let us take an example that a cap x is equal to small a into x, which is represented as equation 3. Generally, an operator will have a set of eigenfunctions and eigenvalues, and it can be indicated as that a cap psi n is equal to a n psi n, which is represented as equation 4. So, in any experiment designed to measure the observable corresponding to a cap, the only values we found are a1, a2, a3. The set of eigenvalues a n of an operator a cap is called the spectrum of a cap. It is very important. Now, let us take Schrodinger equation as an example. H cap psi n is equal to E n psi n, which is represented as equation 5. The solution of this equation can give us the value of E n and psi n. Now, from the particle in a box, we found E n is equal to n square h square by 8 m a square. Now, postulate 3 states that if we measure the energy of a particle in a box, we shall find one of these energies and no others. It is worthwhile to mention that Schrodinger equation is just one of the many possible eigenvalue equations, as there is one for each possible operator. So, equation 5 is very important because the energy spectrum of a system is one of its most important properties. From the equation delta E is equal to h nu, we can see that the experimentally observed spectrum of the system is intimately related to the mathematical spectrum. This is the motivation for calling the set of eigenvalues of an operator as its spectrum, and this is also why the Schrodinger equation is a special eigenvalue equation. Now, I will explain postulate 4. Now, if a system is in a state described by a normalized wave function psi, then the average value of the observable corresponding to a cap is given by average a is equal to minus infinity to plus infinity psi star a cap psi theta, which is represented as equation 6. According to postulate 4, if we are to measure the energy of each member of a collection of similarly prepared systems, each described by psi, then the average observed value is given by equation 6 with a cap is equal to h cap. Let us consider that psi is an eigenfunction of the operator a cap, and also consider psi is equal to psi n, where a cap psi n is equal to a n psi n. Then average a is equal to minus infinity to plus infinity psi n star a cap psi n d tau is equal to minus infinity to plus infinity psi n star small a n psi n d tau is equal to a n integration minus infinity to plus infinity psi n star psi n d tau is equal to a n, which is represented by 7. Furthermore, if a cap psi n is equal to a n psi n, then we can write a cap square psi n is equal to a cap first bracket a cap psi n is equal to a cap first bracket small a n psi n is equal to small a n bracket a cap psi n is equal to a n square psi n, and show average square is equal to minus infinity to plus infinity psi n square sin star a cap square sin d tau is equal to a n square, which is represented by equation 8. Now, from equation 7 and equation 8, we can see that the variance of the measurement gives very important value, that is called sigma a square is equal to a square average minus a average square is equal to a n square minus a n square, that is equal to 0. Thus, as postulate 3 says, the only value that we measure is the value a n. Often, however, system is not in a state described by an eigenfunction, and one measures a distribution of values whose average is given by postulate 4. Now, I will explain postulate 5, which is normally dominated by or described by time dependence of wave function, which is governed by the time dependent Schrodinger equation. Now, what is postulate 5? This is telling that the time dependence of wave functions, which is governed by time dependent Schrodinger equations, though it cannot be derived at this moment, but we can simply postulate its form and then show that it is consistent with the time independent Schrodinger equation. Now, postulate 5 says the wave function for state function of a system evolves in time according to the time dependent Schrodinger equation. So, we can write that h cap psi x t is equal to I h cross dy by dt, which is represented by equation 10. For most systems, h cap does not contain time explicitly, and in this case method of separation of variable technique, and we can write capital psi x t is equal to small psi x into f t. If we substitute this into equation 10 and divide both sides by small psi x f t, we may obtain very important equation 1 by small psi x h cap psi x t is equal to I h cross by f t into d f by dt, which is designated by equation 11. If h cap does not contain time explicitly, then the left hand side in equation 11 is a function of x only, and the right hand side is a function of t only, and so both sides must equal a constant. Now, if we denote the separation constant by E, then equation 11 can be written as h cap psi x is equal to E psi x, which is known as equation 12, and del f by del t is equal to I by h cross into E into f t, known by equation 13. Now, in view of equation 10, equation 12 can be considered as time independent Schrodinger equation. By integrating equation 13, we can get f t is equal to e to the power minus I t by h cross. Now, it is known and so psi x t is of the form capital psi x t is equal to psi x into e to the power minus I t by h cross. Now, it is known that E is equal to h nu is equal to h cross omega. So, equation 13 can be written as capital psi x t is equal to psi x into e to the power minus I omega t by h cross, which is known as equation 15. It is important to mention here that equation 15 oscillates harmonically in time and is characteristics of wave functions, wave motions. Yet, the time dependent Schrodinger equation does not have the same form as a classical wave equation. The Schrodinger equation has a first derivative in time, whereas the classical wave equation has a second derivative in time. Nevertheless, the Schrodinger equation does have wave-like solutions, and for this reason quantum mechanics is called wave mechanics. There can be a set of solutions of equation 12, and so we can write equation 14 as capital sin x t is equal to sin x into e to the power minus I t by h cross, which is represented as equation 16. Now, if the system happens to be in one of the eigenstate given by equation 16, then capital psi star n x t, capital psi n x t dx is equal to psi n star x psi n x dx, which is represented as equation 17. Thus, the probability density and the averages calculated from equation 16 are independent of time, and the capital psi n x are called stationary state wave functions, which are of central importance in chemistry. Now, I will explain postulate 6. The total wave function must be antisymmetric with respect to the interchange of all coordinates of one fermion with those of another. So, electronic spin must be included in this set of coordinates. The Pauli exclusion principle is a direct result of this. Antisymmetric principles and Slater determinants provides a convenient means of enforcing this property on electronic wave functions. In 1926, Born interpreted that psi star psi r is equal to mod psi square, which is the probability density of the particle, and psi r star psi r d tau as probability being in the infinitesimal volume d tau and at the point r. Psi r t and its first derivative must be single valued, continuous and finite. Postulate 1 tells us that the state of a quantum mechanical system is completely specified by function psi r t that depends on the coordinates of the particles and on the time. Postulate 2 states that for every observable in classical mechanics, there corresponds an operator in quantum mechanics. Postulate 3 deals with the measurement of the observables associated with the operator. Now, postulate 4 states and deals with the measurement of the average value of the observable corresponding to an operator. However, postulate 5 states that the time dependence of wave function is governed by the time dependent Schrodinger equation. Finally, postulate 6 emphasizes that all electronic wave functions must be antisymmetric under the interchange of an electron. Now, thank you for your kind attention.